Hi class, I'm not feeling well, so I'm not going to be on campus today. Here's a video lecture so that we don't get behind in our material. Where we're going to start with this lecture is chapter 20, which is electric potential and electric potential energy. In the picture here, it's taken from a medical TV show. There's a person has a defibrillator and is getting ready to use it. So they press the button and it starts to charge. Then what happens is it stores energy. That takes a few seconds. Then they put it on the patient's chest, press the buttons again, and it releases. And it releases current going through the body. That stops the heart, and then the heart restarts on its own with the proper rhythms. So when you first press the button, it starts to store up energy. You might ask the question, what kind of energy? We know it's plugged in and it gets a charge. You know, they say charging. So the kind of energy it's storing is electric energy, and that energy is potential energy. So this is an application of electric potential energy. Before we get started on this chapter, I would recommend you do just a little bit of background reading. Chapter 8 from the textbook, sections 2 and 3, those are pages 228 to 234. That's just a review of gravitational potential energy. I'll go through it reasonably quickly in the next couple of slides, so this should just help make sure you know exactly what's going on. So the same way we used force due to gravity to develop force due to electric field, and we compared gravitational field to an electric field, we'll do the same thing with energy. We'll compare gravitational potential energy to electric potential energy and come up with how we describe electric potential energy. Next, just to give yourself a reminder about conservation of energy, because we'll be talking about that in this chapter as well, I would suggest you go to a PhET simulation. If you Google PhET, P-H-E-T, potential energy, you can use that simulation to show how we switch from having gravitational potential energy when we're up high to kinetic energy as we move down and start to go faster. We'll be doing things like that with electric potential energy as well. So if you use this simulation, it might just help refresh your memory about how you can switch back and forth between kinetic and potential. Chapter 8 then gives a recap of gravitational potential energy. I'll just discuss very briefly what's in that chapter. It discusses how potential energy and work are related, and I'm just going to play this PhET simulation as we go through. So what we know about gravitational potential energy is when we lift something up in the air, so if we raise something up in the air, the work done on it by gravity is negative. And it's negative because if you lift a mass up in the air, the force on it points down. That's the force due to gravity. But the displacement is up. That's delta R. And we remember that work is equal to force times displacement times the cosine of the angle between them. So if they're in opposite directions, the work is negative. The other thing we know, and you can see this in the pie chart as the skater goes up and down on that ramp, as something goes up in the air, the potential energy gets bigger. Okay, so the work done is negative and the potential energy gets bigger. The flip side is if something is lowered through the air, the work done by gravity, so if we lower a mass through the air, the force due to gravity still points down. The displacement as we lower something is down. The work is force times displacement times cosine theta. This guy is positive because they're in the same direction. Okay, whereas when we were lifting it, it was negative. We also know that as something comes down, and that's what's happening into the video right now, as something goes down, the potential energy decreases. Okay, so now that's something we discussed. So when we go from high to low, we get a smaller potential energy. So when we go with the force, the potential energy decreases. When we go from low to high, we get a bigger potential energy. So if we go against the force, we get a bigger potential energy. A definition we had in chapter 8 was that our change in potential energy, gravitational potential energy, was equal to the negative of the work done by that particular force. So for gravitational potential energy, the change in that is minus the work done by the force due to gravity. You may or may not remember your equation for potential energy was U gravity equals m times g times h, where m was the mass of the object, g is 9.81, and h stands for height. Some textbooks use y, I'll stick with h. So what we're going to talk about coming up is what is h, what is it relative to? We're going to talk about how energy and work is force times position and how that relates to electric force and electric field, and we're going to use those ideas to build the electric potential energy. Let's get some notes added about gravitational potential energy. The symbol for gravitational potential energy is UG. And we find gravitational potential energy by multiplying the mass m times g, 9.81, times height h. That's the gravitational potential energy when a mass m is up in the air at some height h. So now we have to be careful here. What does h mean? H means the height above ground. You're pretty much allowed to pick ground wherever you want to be. We normally pick ground to be on the actual ground. So we call that y equals 0. And our y-axis we would normally take as positive pointing up. So our y direction is positive up. Let's think about the motion. If we have some mass m and we let it go, it's going to move down towards lower gravitational potential energy. So that's worth writing down. So if we release, and that means release from rest, if we release mass m from rest, it's going to move towards lower gravitational potential energy. And I'll just write UG for gravitational potential energy. That's true of lots of examples you can think of. If you have a car at the top of a hill, give it a little push, it's going to roll down to the bottom of the hill. If we want to get something higher, we have to apply a force to it. We have to put work into it. So if we want to increase the gravitational potential energy, we would have to do work. Okay, let's apply these ideas to electric potential energy and see what we get there. So let's start with the symbol. Electric potential energy, like all potential energies, has a symbol of U, but electric potential energy would have a subscript of a little e. The units of electric potential energy are the same as the units of all the energy, which is joules. That has a symbol of J. So how do we find what electric potential energy is equal to? Well, let's momentarily go back to our gravitational potential energy. You see that gravitational potential energy is m times g times h. I'm going to put brackets around my mg, multiply by my h. So we see that gravitational potential energy is force times distance. It's the same deal with electric potential energy. Electric potential energy, and I suppose instead of distance, I should be really careful here with the names of my vectors. It's force times position. My electric potential energy will also be force times position. I just have to be careful here to use the correct force and the correct position. The force that acts on an electric charge is the electric force. That's Q times E. And the position, we didn't call that H or Y anymore. We called that S for position. So the reason we use S instead of Y is because if we have something that has an electric field, like a battery or some capacitors, we can turn them around, right? We don't always have to have the negative on the bottom. I could flip a battery upside down, no problem. So I'm going to call my position S, and that's a very typical thing to do. I do need to have a place that I'm going to call ground, or where I'm going to call S equals 0. Anytime you have a coordinate system, you have to put in your origin. I'm going to call S equals 0 at the negative plate. And then my increasing S will go away from the negative plate. Okay, so it still looks like my gravitational potential energy. I'm just using S instead of Y. So now let's make a note of what S stands for. S is the position of the charge relative to the negative plate. So you always have to make sure you know where your ground is or where your zero is. So we know what the motion of a mass is. What's the motion of a charge? That's a good thing to look at next. So let's say we have a positive charge and it's in this area with an electric field. Which way is it going to move? Well, this positive charge is going to feel an electric force that points down. Let's draw that force. So there's the electric force, and we know that the electric force is charge times the electric field. My charge is positive, my electric field points towards my negative plate, so my electric force is towards my negative plate. So if I release my positive charge Q in an electric field, my charge particle is going to move down or towards the negative plate. So let's make a note of that part. So if I release a positive charge, I'll just say POS for positive, we know that the force is equal to Q times E. So the force is parallel to the electric field. Tells me that my positive charge moves towards the negative plate. What does that tell me about my electric potential energy? Well, where my charge starts, so at the initial position, where my charge is initially, my initial electric potential is Q times E times the distance. My final electric potential energy is Q times E times my final distance, which is 0. So my positive charge, when released from rest, still moves towards lower electric potential energy. So my electric potential energy, UE, gets smaller. Now, one big difference between mass and charge is that charges are allowed to be negative. So we never talk about negative masses because that's not really a thing except for maybe on Star Trek, but charges are definitely negative. What happens to those? Let's take a negative charge and let's put that in our electric field. So I'm going to take a negative charge right here. So I'll do that guy in purple. There's a negative charge. What happens to that guy? Well, it feels an electric force. The electric force is equal to the charge minus Q because it's a negative charge times the electric field. So if the field is down, then the force is up, and that negative charge is going to move towards the positive plate. So let's get that in our notes. So if we release a negative charge, it will move towards the positive plate. So the electric force on it is minus Q times E, moves towards the positive plate. What happens to the electric potential energy? Well, the electric potential energy right here is equal to the charge minus Q times the field E times the position S, which is 0. So the electric potential energy starts at 0. When it gets up here, when it gets all the way to the positive plate, the electric potential energy is the charge minus Q times E times the distance S, however far it traveled. So the electric potential energy goes from 0 to some big negative number, maybe like minus 100 or something, or minus 1,000. Minus 100 is smaller than 0, so the charge still moves towards lower electric potential energy. So UE still gets smaller. That's true of all things moving kind of with forces and associated potential energies. Objects released from rest, no matter what they are, they'll always move towards lower potential energy. Okay, so that wraps up our summary of electric potential energy. Let's get a few more notes on it and let's introduce a new concept that's called electric potential.